Okay. Hi, everyone. Welcome to lecture 8, the second lecture on neural network theory. So there's a couple of announcements. We posted homework 3 on the website, and that's due next week on Thursday. And then another announcement is Ugo and I have both been posting references on the website. So to find them, they're under like the sub page for each part of the course. There's like additional papers and additional reading if you're interested. Okay, so today's lecture is about network function spaces. So last lecture, we were kind of looking at different architectures and principles of building the architecture. And this lecture is about, you imagine that you've already got an architecture and you're interested in what kinds of function does this architecture implement. So we're going to talk about a few different topics. We're going to begin with like a general discussion of like the complexity of different functions and what that has to do with machine learning. We're going to briefly mention an idea you might have heard of, that neural networks are universal function approximators, meaning they can implement any function. We're then going to move on to look at, well, what are the typical kinds of functions that the network implements? Like, it seems like it's too good to be true that it can usefully implement any function. So what kinds of function is the architecture biased towards? And then that's going to be the main topic of the lecture, is this formal result, which is an equivalence between neural networks and Gaussian processes. So that's going to be the main thing that we're going to try and understand in this lecture. So let's begin. So what does a neural network's function space look like? So kind of a vague question to begin with. So, you know, like a more specific question is, how complex are the functions implemented by the neural network? So what does complexity mean? It's not really clear at this point. So an example that people give is starting out with regression, and you imagine that you have, you know, you've got a data set that you're trying to, you've got some data points that you're trying to fit. And you imagine to begin with that they sort of look, it looks kind of like a linear relationship, but there's some deviation. And one thing that you could do is you could fit a linear, you could do linear regression and you fit a linear curve. And you could argue that in a sense, this is kind of like a simple curve. But of course, you could do something else, which you could take a much more complicated function class, like a high order polynomial or something like that. And it could actually go through all of the points. And intuitively, you would call this a complex function. In this lecture, we're going to focus more on classification. So I just want to like construct the analogous example for classification. So for this, we need some axes. And let's say that X is the input space, and that there's binary labels. So an input can either have a label +1 or a label -1. And let's say that we have data points, which, you know, for this part of the input space, they get label +1. And for this part of the input space, they get label -1. But there's some outliers in the data, so there may be a point here. Well, then the analogy of a simple function would be something which is, you know, it's like positive in this region and then it goes negative. And we might say that this is somehow simple. And the analogous complex function would kind of look the same here, and then it goes negative, but then maybe it like becomes positive here and then it goes back down, and we would call this one complex. but we're still being very vague. This is just to express the intuition that we have some hope that when we find a function in machine learning, it's at the right level of complexity to not kind of fit spurious relationships, but fit the true relationships. But this is really vague. And we're going to be concrete about what we mean by simple and complex in the lectures on generalization theory. But for now, we'll just remain vague. But it seems like intuitively there's something bad about having these super complex functions that can fit even spurious relationships. And it seems like the situation only gets worse because of something called universal function approximation. So this is a set of theoretical results, which I'm just introducing informally on this slide. But there are theorems which say things like a wide enough neural network can fit any function. Like a neural network, that's what it means by a universal function approximation, that the network can realize the entire universe of functions, meaning it can realize all functions. And that may seem like a theoretical result which doesn't have anything to do with reality. But when people run experiments on this, they make empirical findings, and what they actually find is that they can give the training set like arbitrary training labels, and the neural network can fit that arbitrary labeling of the data. So universal function approximation isn't just like this theoretical thing which doesn't happen in practice. Like neural networks actually are immensely, they have an immense capacity to fit almost arbitrary functions. And I'm going to give more examples, actually concrete examples of this when we get to generalization theory. But for now, I just wanted to, say that these neural networks are immensely expressive. They can fit arbitrary labelings of many common data sets. But what I want to say now is that what this doesn't say is sort of what kinds of function does a neural network like to implement. So it may be the case that in principle, there's one very particular setting of the weights which realizes one particular function, but that doesn't mean that that function is somehow common in the function space. So another way of saying this is what kinds of function are common. And if you think about it, like which kinds of function are common in the function space, or what kind of functions the network is biased towards implementing, that's a way of trying to get at this thing called inductive bias. Which again, we're going to be vague, but what I'm trying to say is that although the network may be able to implement almost arbitrary functions, there may be certain kinds of functions and that it prefers to implement, and those may be the kinds of functions that we're actually interested in. So that's what we're going to try and develop the tools for understanding in this lecture. Okay. By the way, yeah, I'm going to try and stop more and ask if people have questions, or feel free to just interrupt me if you have a question. Okay.
Actually, I have one question. Does the theorem depend on the function that you use in the neurons?
You mean like the nonlinearity?
Yeah.
There are theorems, I think, which make very mild conditions on the nonlinearity and still hold. So it's not, the theorems on the universal function approximations aren't approximation theorems, aren't like super sensitive to the nonlinearity.
Thanks.
Yeah, I could include a bit more on that in in the lecture on generalization theory, but yeah, this lecture is somehow a bit orthogonal to this idea of universal function approximation because well, anyway, you'll see. Okay, so to get at this question of what kinds of functions does the network like to implement, we're going to do something which is called moving from weight space to function space, because it's going to turn out to be sort of intractable to ask these questions in weight space. But if we actually study the functions directly in function space, then we can answer some of these questions. So what does this mean, moving from weight space to function space? So you imagine that you have this thing called weight space, and what that means is that, and I'll label this with the symbol omega. But what that means is that a point in weight space, a point W, is a weight vector. So we have a weight vector W. And to map this point to function space, what we mean by that is that we take a finite set of training inputs, or a finite set of inputs, x1 up to xn, and we construct a vector of outputs. So if we have a network F, we pass in input 1 with weight vector W, and that's okay. And then we pass in all n of these inputs and we get n outputs. And we're going to define this thing, this vector, to be our function space representation. So this is our weight space representation. It's just a weight vector. And this is our function space representation, which is just a vector of outputs. And the reason that this is useful, well, the first reason is that, well, function space, what you usually think of as function space, is infinite dimensional, because there are an infinite range of inputs, so there are an infinite range of outputs. But if we restrict to studying the function on a finite set of inputs, then what we're meaning by the function space representation is finite dimensional. If there are n inputs, then it's a vector of length n. So this is going to be a useful thing. And to visualize function space, well, you can imagine that our set of inputs just contains 2 inputs. Then you can plot function space in 2D. So on this axis, we have f of x1 with a particular weight vector. And on this axis, we have f of x2 with a particular weight vector. And like, if this is the weight vector that we've chosen, this point, then that corresponds to a pair of outputs. So we could plot that like this pair of outputs. And you can imagine moving this weight vector to this other point in weight space. And you can think that that's going to have the effect in function space of moving the outputs of the network. And in this example, what I've represented is that by moving the weight vector from this starting point to this end point, in this case, we've actually crossed the boundary in function space where the output on input 2 has gone from being negative to being positive at the end. So this is what we mean by going from weight space to function space. And there's a couple more reasons why this is actually a useful thing to do. So the idea is that life is simpler in function space. So one of the reasons is that if you have a weight vector W and another weight vector W prime, when you look at things in function space, they can actually be the same point in function space. So the idea is that many weight vectors can map to the same function. So if you're thinking in weight space, you have to worry about making sure to count all of the weight vectors that realize the function you care about. But if you work directly in the function space, you don't have this issue of making sure you count all of these things. And counting those things is really hard or essentially impossible.
I have a question.
Oh, please, yeah, go ahead.
So if multiple weight vectors can map to the same function, does that mean not all the like items in the weight vector are being used, or it's only for certain like inputs that they're the same? Because it kind of seems like if you were using all of the weight vectors, I guess maybe by symmetry. I'm just trying to think about how that's possible.
Right. So yeah, it can happen for more than one reason. You're right. Like the first reason is like there are symmetries in the network, like you can permute the hidden nodes within a layer and it doesn't change the function at all. So that would mean that the function is the same on every single input.
Oh, I see.
So that's one kind of way this can happen. Another way is because we're just looking at functions on two inputs here. So it could be the case that the functions are the same on these inputs, but different on other inputs. But because we're only looking at these inputs, we wouldn't notice that.
Oh, I see. Okay.
So yeah, there's two ways it can happen.
Scale across layers.
Oh yeah, and there's other symmetries that are, yeah, exactly. Like you can scale up one layer and you can scale down another layer, and in ReLU networks that doesn't change the output. So there's many symmetry. There's many kinds of symmetries which right, for every point in weight space, you can do this permutation and it gives you another point which is exactly the same in terms of function. And you can also do rescalings of scale up one layer and scale down another layer. There's all kinds of symmetries like that.
Okay, thanks.
Jeremy, just to clarify, so these slides and the last slides, I will assume you are focusing on the over-parameterized neural networks, right?
I haven't really said how many parameters there are, but what you're asking is like, given a weight vector W, like how many, like what you're basically saying, what is the dimensionality of weight space? Like it could be that it could be that omega is equal to like a Euclidean space of dimension n, or like, yeah, or some dimension d. And I haven't mentioned what d is so far, so it could be low or it could be high, but that's not important to have this picture that we're developing at the moment. We're going to take it really high later on in the lecture. But yeah, I guess we haven't got there yet.
Gotcha.
Okay. The second reason is that geometries that we care about may be simple in function space, but really complicated. Like intractably complicated in weight space. So what that means is that later on when we do generalization theory, like something that we're going to be interested in is quadrants or orthants of function space. That means we're interested in all functions which have a particular sign of their output. And in function space, this is just a quadrant, which is like, easy to describe. That's a simple thing. But if you try and map this back to weight space, you have no idea what that looks like. It can be like this really complicated thing that you can't characterize, but it's easy to characterize in function space. So that's another reason that we would like to move to function space if we can. So then the question is, well, how can we get there? Like, how can we describe functions in function space? At the moment, everything's been completely abstract. So the idea that we're going to have is we're going to think about randomly sampling weight vectors and inspecting the function that we get under random sampling. So to illustrate that idea, what I want you to imagine is that you throw a dart at weight space, and it's going to like land somewhere totally random in weight space. Let's say it lands here, and this is a weight vector W. Then we can now inspect the function we get. And what you think is that that corresponds to like hitting some point in function space. So remember that the axes here, it's like the network input 1 with weight vector W, where W is right, where the dot landed. And then the next thing I want you to imagine is that you just keep throwing more darts. So we throw more darts. And like, let's say the first one hit here and that corresponded to this function. And then let's say we hit here and that corresponded to this function. And we keep throwing out more and more darts. And we sort of build up this picture of what kinds of functions the network likes to implement just by sampling lots and lots of functions and seeing what they look like. So thinking about universal function approximation, like that says that the network is capable of implementing some really weird functions. Like, but the idea here is that maybe, let's say there's a really weird function at this point in weight space, and it like in function space, it ends up like somewhere over here. If that function is really weird, but also really rare, then you're almost definitely not going to hit it when you're sampling random functions, if that makes sense. When you're sampling random weight vectors, you're never going to hit this yellow point.
Well, I have a question.
Oh, sure, go ahead.
So when you like randomly selecting a weight, like if you pick a weight, you specify a function, right? Then why does that only become 1 point on the function space thing?
Right. So it sounds, I think maybe what I haven't explained well is what this function space means. So what it means is that let's look at say picking this weight vector and it lands at this point in function space. What that means is that this point is a pair of outputs with coordinates.
I see. Yeah, okay. So yeah, I see now. That makes sense.
Okay. So what I'm going to show you next is an example of actually doing this process and what actually happens. So hopefully this will make everything clearer as well. And like, to understand the rest of the lecture, it's quite important that you understand what's going on in this slide. So let's like take some time and ask questions and stuff. And I put the code to generate this slide on the website. So if later on you're curious to explore it a bit more, there's code to do that. So what's going on here is I take 4 inputs. So input 1, input 2, input 3, and input 4. And these are just images of trucks and like with varying amounts of noise added to the image. So that's what you're seeing. And then what I did was I took a multi-layer perceptron with 3 layers. And the width of the hidden layer is 1,000. And there's 1 output unit. And so what that network looks like, if you imagine the network, it's like there's an input layer, there's a hidden layer with 1,000 hidden units, and then there's an output layer with 1 unit. And you know, it's all wired up. And this network has it's using the ReLU nonlinearity. And then that's like the output weights. Okay, and then to get these plots, like let's first of all look at this plot. What it shows is the vertical axis is output on input 1 of this network, and the horizontal axis is output of input 2. And then what I do is I randomly sample weight vectors, and every time I sample a new weight vector, I plot the outputs of the network for this pair of inputs with that weight vector. So I'm doing this process of I'm throwing darts at the weight space and I'm getting points on function space. So like, does everybody, like, is it clear what this scatter plot is? Because, yeah, okay. And then, just interrupt me if it's not. This scatter plot is the same thing, but for input 1 and input 3. And this scatter plot is the same thing, but for input 1 and input 4. The key observation, or like the thing which should be surprising if you've never seen it before, is that these scatter plots look like, you know, like a Gaussian distribution. Each one looks Gaussian. So the outputs look Gaussian. And it's like not clear immediately why that would be the case. Why do the functions implemented by random neural networks look Gaussian in output space? And the second observation is that, like, notice that this Gaussian is like super highly correlated. It looks almost linear, whereas this Gaussian is like the scatter is much broader. Like in this direction, there's a lot more scatter. So you notice that when the two inputs, input 1 and input 2, are very similar, the outputs are highly correlated. That makes sense because if the input was the same, then the outputs would be the same. So it would be perfectly correlated. And when the inputs are different, like this one and this one, you get more correlation.
I think it's kind of shocking how correlated the outputs of input 1 and input 4 are.
Yeah.
There's so much noise in input 4.
Right. Do you see that you actually can still see the truck if you just like, I don't know, if you like look at the truck and then you like look here, you can still see it, but like it just kind of, you can tell it's there if you know it's there. Like there's a little white corner here and that corresponds to like this.
Jeremy, I have a question. So for human, it's very easy to tell the gap between input 1 and input 2 is way smaller than the gap between input 1 and input 4. I'm wondering,
Right.
for neural network, what is the right notion of distance, like between two inputs? Like, is this something like two norm, or like some kind of norm between two pixels?
That's a great question. That's like what the whole lecture is about. So yeah, we're going to show actually how to analytically compute this correlation structure and this correlation structure.
I see, but here in this slide, like neural network is consistent with human in a sense that, like,
right.
I see.
Yeah, that's a, like, I could just tell you now, but I think it's better if we just like do the lecture and like build it up gradually. But yeah, something to mention is that because of the fact that this is a ReLU network, it's going to turn out that that you're always going to get positive correlation. Because like the representation at the final hidden layer is always positive because the output of ReLUs is always positive. So I think that it's partly why what Yisong said about being shocked about how much correlation there is that actually for a ReLU network, what we'll see later on is that you actually always get positive correlation. And that's because of the fact that the outputs are always positive. So like, yeah, anyway. I think if you have a different kind of nonlinearity, then you can get less correlation. But so, okay, just to recap, it's like things in function space look Gaussian. It's not clear why. And the rest of the lecture is going to be like deriving this result theoretically and like trying to understand why analytically. So yeah, like please ask more questions at this point and Otherwise, I'll keep going.
I have a question. What kind of noise did you apply to the picture? Like what was the difference there? Like
I just added Gaussian noise, and then I truncated it if it went out of the the valid range of colors that are allowed in an image.
Okay, cool.
But yeah, but actually the details are not like, actually what we're going to see is that the only thing that this correlation structure depends on is like the degree of like actually the inner product between these images. So maybe that answers Guanya's question. And then actually that inner product gets modified by the network. So if there were no hidden layers and it was just a linear layer, like one layer or one linear neuron, actually the correlation, we're going to show this in the lecture, but if it was just a linear neuron, the correlation would only depend on the inner product between the images. So like just the Euclid, like, like the standard dot product.
So it has nothing to do with the fact that the noise is Gaussian?
No, it doesn't depend on that, yeah. And so in the homework, I'm going to get you to, the homework that's posted, you're going to verify this, the theoretical result for this covariance. And it's going to be, the notebook I did uses these images, but if you want to sanity check that, you could put in arbitrary images into that notebook, and you could test that this result still holds. Okay. So if things look Gaussian, the important thing to realize is that for a Gaussian with mean 0, which actually that was, the entire distribution is summarized by the covariance matrix. So like the covariance summarizes the distribution. There's no other parameters in the distribution. So what is the covariance in this case? Let's write it as sigma ij, and what this is going to denote, like, well, let me just write out the formula. It's the expectation under sampling weights randomly from some measure on inputs on weight space. Like, for example, it was from a Gaussian, we were sampling weights Gaussian. And then it's the output on input I for weight vector W multiplied by the output on input J for weight vector W. So is this clear that we're defining sigma ij to be the covariance between the output on input I and the output on input J under random sampling of the weights. And right, but the covariance takes this simple form because we know the mean is 0, or if the mean is 0, this is the form of the covariance. So this is what we're going to be concerned with for the rest of the lecture, is deriving analytical results on this covariance, or first of all showing that things are Gaussian with mean 0, and then getting this covariance. So before we start that whole process, I just want to now, we showed you an example of this behavior, I want to state something a bit more formal, but still not completely formal. But so the claim is that wide enough neural networks are Gaussian processes, or act as Gaussian processes. So what this means is for a finite set of inputs, x1, x2 up to xn, then what you do is sample a weight vector W from some simple distribution. For example, like the components of W are IID Gaussian. then the claim is there's a couple more conditions which are right. The network has to be wide enough. Then the result is that the outputs are jointly Gaussian. So what that means is that this thing that we called the function space representation is normally distributed with some mean and some covariance that we're going to compute for special cases. But this is the statement. The way this goes beyond the example is that the example I was just showing you pairs of inputs because you can visualize that easily on a scatter plot. But this is now holding for arbitrary numbers of a finite number of inputs, but the number of inputs is arbitrary. So this is the technical statement, and like we're calling it a Gaussian process, but maybe you don't know what a Gaussian process is. But let me just show you the formal definition of a Gaussian process, and you'll see that this is why this is a Gaussian process. So a Gaussian process is defined formally as something where if you take any finite collection of inputs, then if the function outputs are distributed Gaussian, then this thing is a Gaussian process by definition. So this is the definition of a Gaussian process. Any finite collection of inputs, the outputs is a Gaussian random vector. So that claim about neural networks is just claiming that they are a Gaussian process by definition of what a Gaussian
claim about neural networks over a randomized process for generating the weight vectors.
Right, exactly. Yeah, so under these two conditions, then the neural network function is a Gaussian process. Okay, so if you want to prove this result, what you need to do is you need to prove that for a finite collection of inputs, under some like conditions which we can impose, you need to prove that the distribution of outputs is normal. So that's the process that we're going to go through now. But so to establish that something's a Gaussian process, you show that the outputs are normally distributed for any finite collection of inputs. So to do that, right, to prove this claim, we need some Gaussian facts. These are like things that not everyone may know about Gaussian distributions, but you need them for this lecture. So we're just going to go over them quickly. The first thing we're going to need, well, one of the things we're going to need is the central limit theorem. So I'm stating it here, but let's like walk through it. So it assumes that we have a collection of random variables, n random variables, their IID, and each, for simplicity, has mean 0, and it has a finite variance sigma squared. Then what we're interested in is like the limit that n goes to infinity. So we have an infinite number of them. We define x bar to be the mean of the random variables. And can anyone tell me what this tends to as n tends to infinity?
Zero.
Yeah. Thanks. So this tends to 0 with probability 1, which means that technically it may not go to 0, but with probability 1, yes, it goes to 0. And that's just like the law, it's called the law of large numbers. And then the idea is, because this thing goes to 0, well, let's scale it up by a factor of root n to try and stop it going to 0. So like now this thing is going to go to 0, but this thing is going to become large when you make n large. And like how does anyone know how this thing behaves when you make n go to infinity?
It will become a Gaussian, standard Gaussian.
Right. So this in distribution converges to a Gaussian with variance sigma squared. So this is just the formal statement of the central limit theorem that the properly scaled mean converges to a bell-shaped curve. But if you don't properly scale it, you're going to get something different. For example, this scaling gives you 0. Okay, so you add up independent random variables and you get a bell-shaped curve. That's the central limit theorem. We're actually going to need a more advanced result, which is called the multivariate central limit theorem. So what this says is that instead of x's being random variables, we have y's, and they are random vectors, which are IID. And the mean of each vector, the distribution of each vector is the same because they're IID. And let's say y1 has mean 0, but this 0 is actually a vector of zeros because y is a vector, and y, the components of y1 have covariance matrix sigma. So this is the preconditions of the, and the covariance has to be finite. Then as n tends to infinity, the mean vector, so yi's are vectors, it's basically the same result, but it tends to the vector 0 as n tends to infinity with probability 1. And now you scale up the mean to try and prevent it from going to 0. And this thing converges to a normal distribution, multivariate normal with mean 0 and covariance matrix sigma. So this is the statement that you add up IID random vectors and you get a random vector which has multivariate normal distribution. So we're going to need this. And like to give you a hint of why we need this, we're like, this a neuron sums over lots of inputs, and that's why we're going to want this kind of result. But anyway, okay, the last fact that we need is that about the linear transformation of a Gaussian random vector. So let y be a random vector that's Gaussian. Does anyone know what the distribution of AY is, where A is a fixed matrix? Or can anyone tell me anything about AY? Like, don't worry if you can't, because I didn't know this.
Normal mu A and A prime sigma A.
Yeah, okay, that's good. Yeah, so that's what we need, is that if you take a random vector and you linearly transform it with a matrix, then the distribution is normal with mean AY and covariance. It ends up being A sigma A transpose. So that's the result, that if you multiply a Gaussian random vector by a matrix, it stays Gaussian. It just changes the mean and the covariance. If you want to know how to prove, okay, just take that as a fact for the lecture, because we're going to need that as a fact. But if you want to know how to,
A mu.
Oh yeah, sorry, thanks. Yeah, good point. Yeah. If you want to know how to prove this, it's the simplest way is by moment generating functions. So the moment generating function of y is defined to be the expectation of e to the t transpose y, where t is a dummy vector. And if you evaluate this, it becomes equal to t transpose mu plus half t transpose sigma t. And the fact you need to know is that a moment generating function uniquely picks out a distribution. So this is the unique moment generating function of a Gaussian with mean, mu, and covariance sigma. And then if you compute the moment generating function of e to the t transpose ay, you basically substitute ay in place of y into this, sorry, you substitute t transpose a in place of t and t transpose into this result, and you find that this is equal to e to the t transpose a mu plus half t transpose sigma, sorry, a sigma a transpose t. And because this uniquely, and then you basically recognize this as the moment generating function of a Gaussian with mean a mu and covariance a sigma a transpose. But if you didn't follow that, or you don't know what a moment generating function is, just don't worry, just take this thing as a fact. That okay. And on the homework, you're going to need this, but you don't need to like prove this. You can just take this as a fact. Okay. So now we have everything we need to start proving this thing that we call the neural network Gaussian process correspondence. So we're gonna like build up this result in stages. So we're gonna start with a linear neuron. So if you remember, we have some, inputs x1, x2 up to xd. So the subscript is denoting different components of the same input. And we have an output y, which is equal to the sum from I equals 1 to d of wi xi. But now we're going to go a bit further because we're going to have a finite collection of inputs. So we have x superscript 1, x superscript 2, x superscript n. And then what we're going to say is that we're going to sample the weights. Each component of the weight vector is going to be sampled IID Gaussian with some mean and some covariance. Well, actually, okay, with yeah, for now it's just Gaussian. I won't tell you the mean and the covariance, it doesn't matter. And remember that what we're interested in is what is the distribution of outputs, like on input 1, input 2, up to input n, under the random sampling of the weights. So the way to see this is we're gonna start by stacking the inputs into what we call the data matrix. So we define this matrix X to be x1, x2, up to xn, stacked in rows. So we create a matrix where the inputs are the rows of the matrix. Then we can write the vector of the outputs, y1, y2, up to yn. We can construct this vector, and we see that this is equal to x times w. So it's a matrix multiplication. And so the point of this is that w is a Gaussian random vector, and we're multiplying it by a matrix. And as like the third Gaussian fact that we had is that that thing is Gaussian by the whole thing about moment generating functions. But so by that fact, this vector is Gaussian, which means we can conclude this is a Gaussian process. So yeah, feel free to ask questions. If
I think the y should be a column vector, not a row vector.
Yeah, sorry, I guess I'm not being careful about that. Yeah, whichever one it should be. Yeah, sorry, you're right. Okay, so we've shown it's a Gaussian process, but we haven't computed its covariance. So what is the covariance of y is a Gaussian random vector? What is its covariance? So that's what we're going to do on this slide. So to compute the covariance, we can just look at two components of y. So let's look at y1, which is this thing, and y2, which is this thing. And this is a question on the homework, but this is like the reward for coming to the lecture, is that you just get to find out how to do it. So this is the equations for two of the outputs given two of the inputs. And now we actually need to know what the distribution of W is. So let's say that W is distributed normally with mean 0 and covariance sigma squared. Then the mean output is the expectation of, let's look at y1. And this is equal to, you can pull the expectation inside the sum. But that, because the expectation of W is 0, this thing is equal to 0. So the mean output of the linear neuron is 0 because of the fact that the weights have mean 0. And now we can compute the covariance of the output. Which is just, because the mean is 0, this is just the expectation of y1, y2. Which is, like the expectation of the sum over I of wi xi1 times the sum over j of wi xj2. And, you can pull the expectation inside and we get it's the sum over ij of the expectation of wi wj times xi1 xj2. And because of the assumption that the weights are being sampled, each component of the weights is being sampled IID, this joint expectation is 0 unless I equals j, because the different weights are independent and they have mean 0. So this what we have is expectation of wi wj is equal to delta ij, like Kronecker delta, times sigma squared. So like it knocks out a bunch of terms in the sum and you're left with sum over I sigma squared times x1 xi1 xj2, which is just equal to sigma squared times x1 transpose x2. So the covariance of the linear neuron depends on the inner product between the inputs. So to go back to the example, like what does this actually mean? We're starting to see this structure emerging where the correlation depends on like the similarity between the inputs. So in the case of a linear neuron, what we just saw is that it actually only depends on the dot product between the pair of inputs. So let's just go back to that result and just look at it again. Right, so that we're claiming that the covariance between a pair of outputs just depends on the dot product between the inputs. But of course, in that example, that was not a linear neuron, that was a neural network. So this result might not still hold. So let's start building up even more. So now we're going to consider a linear layer, which this one's actually really easy and it may not have been, but the idea is that a linear layer is just, it's just more than one linear neuron. But if the weights of each neuron are sampled independent, let's say, well, we're actually assuming that all the weights are sampled independent, but in particular, the pink weights are independent of the blue weights. That means that the pink neuron is a Gaussian process by the argument we just gave. The blue neuron is a Gaussian process by the argument that we just gave. And if you take two independent Gaussian processes and stack them, it's still Gaussian. It's just saying if you take two independent Gaussian random vectors and glue them onto each other, it's still a Gaussian random vector. So the linear layer is also a Gaussian process. Let's make it a bit harder. So one hidden layer. This is like, now we have something which you can like more comfortably actually call a neural network. And this is the thing that the example was. So we're actually doing that example now analytically.
I have a question.
Oh yeah, go ahead.
It's pretty basic, I guess. Why do we sample the weights as like a Gaussian distribution instead of, say, a uniform distribution or something? If our goal is to understand what the function or what the output looks like.
That's a great question. I think the answer is that you could sample the weights uniform, but you could, and I think the results would all still go through.
Oh,
I think all these results are depending on is the fact that we're relying on independence of the different weights in the way that we're sampling them. And I think that it's a little harder when you do things from a uniform distribution because there's actually a small amount of weak dependence if you sample a random vector uniform.
I guess by the central limit theorem, it would probably still hold. I'm not sure. Okay, that kind of makes sense. Yeah.
Oh yeah,
because
sorry.
You lose the covariance completely. What? Yeah, I guess that means is covariance.
Yeah, like
zero.
For now, when we start actually doing the central limit theorem, you'll see like precisely what conditions we need on the way that the weights are sampled. Okay. But for now, let's just say that like sampling them Gaussian isn't the craziest thing to do.
Right. Yeah.
Okay. So for when we have one hidden layer, oh yeah, sorry, are there any more questions? But yeah, I'll try to highlight that when it's like we're going to do that calculation now. So okay, we have an input X, which has, on this picture, it's got two components. And the way the output is computed is it's a sum. In this case, we've drawn 3 hidden units. So it's a sum over the hidden units, I equals 1 to 3, of UI, where U is the weight on this layer, times a phi of, now I'm going to call the weights that go into this neuron, I'm going to call, that's a vector, and I'm going to call that vector W1, if that makes sense. So this now becomes WI transpose X. So I'm saying that there's 3 weight vectors on the input layer. Right, it's just saying that the input layer is a matrix with 3 rows, if that makes sense. But in general, there's not just going to be 3 hidden units. There's going to be what we'll call D hidden units. So this is going to be the sum from I equals 1 to D. So does this make sense that this is the formula for the output as a function of the input when the nonlinearity is phi, and I'm calling all the units going, all the weights going into hidden unit 1 as a vector that I'm calling W1, and then that vector gets inner producted with the input. So once you have that formula, well, remember that what we're interested in is like we have a finite collection of inputs and we're interested in the distribution of outputs under random sampling of the weights. Finite collection of inputs are x1 up to xn. So I'm going to write the vector of outputs y1 up to yn. And the realization is that you can write this as a sum from I equals 1 to d. So a sum over the hidden units of ui phi of wi transpose x1. So that's just this formula, but I've pulled the sum out of a vector, which I'm writing down. And then ui phi of wi transpose xn. Okay, so I've written the vector of outputs as the sum over the hidden units of, what is this term? This term is the, the output of hidden unit I on input 1. And this term is the output of hidden unit I on input n. So is it clear that like what this equation is saying? I can write the sum, I can write the outputs as a vector, and that is, you imagine putting this equation in here and this equation in here, and then you just pull the summation outside of that vector. So the outputs is a sum of vectors. And then the next realization is that each of these vectors, so for each hidden unit I, we have a different vector. So for the ith hidden unit, let's say this one is the ith hidden unit, we get this vector. The only weights this depends on are the ui's and the wi's. And here there's ui's and the wi's. So for example, if I equals 2, so we're looking at the second hidden unit, it just depends on these weights and these weights. And for this hidden unit, the vector only depends on these weights and these weights. So notice that those are distinct sets of weights. They don't depend, each vector in this sum depends on different weights. And since we're sampling the weights independently, that means that each vector in this sum is independent of every other vector in this sum. So I guess I'll write that because that's like the main important observation. But because this is a sum of independent random vectors. And the other observation is that assuming that the distribution that we sample W1 and U1 from is identical to the distribution that we sample W2 and U2 from, and so on, then not only is this a sum of independent random vectors, but it's also a sum of identical random vectors, or the distribution is identical. So yeah, so all we're relying on is, like I said, that we're sampling them Gaussian, but all we're relying on is the fact that the distribution is identical. And, there's other technical conditions for the central limit theorem to apply, like the variance has to be finite. So, but you'd be crazy to sample them from a distribution with infinite variance. So basically under really mild conditions on the way the weights are sampled, the outputs can be decomposed into a sum of IID random vectors. So that means that if we now take the limit that d tends to infinity, then by the multivariate central limit theorem, the outputs are Gaussian. So that implies, right, this is a Gaussian process. So does anyone have any questions? Or like, I could either try and explain it more, or I could just like move on, or I don't know, are people following?
So is this why you have the like wide enough constraint? It's just so that like D is going to be so large that you can assume that the like multivariate CLT is going to hold well?
Exactly, yeah. So it's so that the central limit theorem kicks in. But it, you know, like in that example with the trucks, that was just, D was just 1,000, which is not like crazy wide, you know, like that's like often you would use a width that wide in practice. So it doesn't have to be like crazy wide for the central limit theorem to kick in.
You were going to mention the conditions on sampling U and W if it's not from a multivariate Gaussian for this to hold.
Right. So all we're requiring, if you think about it, is that the U's and the W's, like a sufficient condition for this to hold is that every single weight component is sampled IID with finite variance. That's all we really need. I guess I'll just write this here. Every single weight, like every individual weight sampled IID with finite variance. That's enough to ensure that every vector in this sum is independent and identically distributed. So yeah, you could sample them uniform. And I think the thing I was, by the way, I guess if you're watching the recording, the thing I was saying about uniform, I just realized it was kind of nonsense about like being weakly dependent. So, but anyway, yeah, this thing is all you really need. The other condition which I didn't mention is that you require that these W's having finite variance. Technically, if phi sent things to infinity, that could blow up the variance, and the variance of this product would no longer be finite. So we for the central limit theorem to hold, you require that the variance is finite. But to get that to happen, you would need to use a really weird nonlinearity. Like it would need to send things, basically, it would need to make things which were finite infinite. So like really this result is holding under very mild conditions.
I think the only thing you need is phi is continuous.
Yeah, something.
I think for that to happen, phi cannot be continuous.
Right. 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 If phi is like tan, if it's the tan function, like tangent function that blows up at pi/2 or whatever, like this result would not hold. But if phi is like ReLU or just something mild, the result is fine.
All right. So continuous and defined over the entire domain.
Yeah. Right. But I'm going to put references so you can find the like formal statements of these results. But I just want you to get from the lecture like the mechanism by which the result holds. Okay, I should go fast because there's, I guess, yeah, there's just a little more to do. So I'm actually not going to prove the result for many hidden layers. I'm just going to like give you a sense for how you would prove it. But it's a little harder than one hidden layer. So the idea is that, let me call, this is a multi-layer network with width D1 for this hidden layer D2, and I'll call this width DL-1. And I'm going to call this hidden unit H1, this hidden unit H2, and this hidden unit is HL-1. Then I take a finite set of inputs. I take I construct the vector of outputs. And I can write this in the same way as I did for the before, as a sum over the hidden units in the penultimate layer of the weight, let's call this U1, U2, up to UDL minus 1 of UI times HI of X1 times UI HI of Xn so I've decomposed the vector of outputs as a sum over hidden units in the penultimate layer of vectors, where, you know, this is right, like for I equals 2, it says what is the output of the second hidden unit on input 1, what is the output of the second hidden unit on input n, and then multiply it by like the weight of the connection that joins this hidden unit to this output. So I decompose it into this sum. The challenge with multiple hidden layers, well, I want to do the same thing that I did on the last slide. I want to be able to say, well, I would like to be able to say, well, this is a sum of IID random vectors. The problem is, it's not clear that it is in this case, because remember on the previous slide, the fundamental mechanism, it was the idea that these weights are independent from these weights, if that makes sense. And this weight going into this hidden unit, those weights are all independent from these weights, and they're all independent from these weights. But if I try and make that argument here, what you realize is that like this hidden unit, what it depends on when you get back to one of the early layers is all of these weights. All the weights in this layer somehow end up influencing this hidden weight, but they also all end up influencing this one. So this claim so we want to be able to claim that that for example, like HI of X1 is independent of HI of X2. Sorry, no, that's wrong. We want to be able to claim that HI of X1 is independent of HJ of X1, meaning that like the first component of this vector is independent for different i's, i.e. for different hidden units. We would, if we could claim that, we would be done, because we can just apply the same argument from the previous slide. And this is for I not equal to j. But for the reason I just mentioned, it's not obvious that that's true, because like this, what we're saying is that this hidden unit and this hidden unit, so two different hidden units for the same input. That's what we're talking about. Two different, this hidden unit and this hidden unit for the same input. They depend on all the same randomness in one of the early layers. So they depend on the same thing. So you shouldn't think that they'd be independent. It turns out that if you take the width of the early hidden layers to infinity, they actually become independent. So it's a surprising result. And I'm not going to go into the details of it, but the idea is that what you do is you work forwards through the network, and you start by proving that for the same input, these hidden units are independent. Then you take this width to infinity, and then you prove that these hidden units are independent. And the way that you prove, assuming that these hidden units are independent, you can prove that these hidden units are independent by applying another multivariate central limit theorem. So given that these are independent random variables, then each of these hidden units is a sum over infinite independent random variables. So it's Gaussian. And then you show that the covariance between two different hidden units within the same layer for the same input is 0. And if it's a Gaussian with 0 covariance, then it implies independence. And that's how you extend independence to the next layer. And then you apply that process recursively, like forwards through the network. I think it's too technical and there's not a lot of time, and I didn't really want to get into the details of this anyway. So I'm just going to put a reference on the course website. And if you're really into this kind of proof, then you can take a look at it. But the main claim is that as long as you take all the hidden layers to infinity, then you have the condition you need to apply the multivariate central limit theorem to this thing, and the output is a Gaussian process. Okay, but I'll put a reference on the website. The final thing, which is in some ways quite important, because it is on the homework, is computing the covariance for MLPs with L layers. So what we're going to do now is I'm just going to present to you the result, but we're going to take a network which looks like this, and it has ReLU nonlinearities for the hidden layers, and I'm just going to tell you what the covariance is, and then on the homework you're going to verify that this result is correct empirically using code which is provided for you. So the statement is we have an L layer MLP and we send the hidden layer widths to infinity. We use a particular nonlinearity which has a particular scaling, which is this √2 factor onto a ReLU. The reason we put √2 there is because it simplifies the form of the result. If we didn't put √2 here, we would have loads of √2s appearing in the result. We have a finite collection of inputs, and we assume that the inputs are scaled to have a certain Euclidean norm. And you're free to do that because you can take whatever the input was and you can just rescale it. And again, the reason that we assume this scaling on the inputs is because it simplifies the form of the result. If we didn't assume this scaling, we'd have loads of square root Ds appearing in the result. And we assume that all of the weights for every neuron in the network are drawn normally with this variance 1 over fan-in. So remember, like a neuron looks like this. It has a number of nodes going into it, and we call that number of nodes the fan-in. Okay, and the claim is I'm not going to prove it. We're going to define a helper function h of t, where t is just a real number. And this is defined to be 1 over pi times √1 minus t squared plus t times pi minus arc cos of t. This is just some function which maps real numbers to real numbers. Okay, then for two inputs, xi and xj, the claim is, or let's call it x and x prime. The claim is that the covariance is given by expectation of, so the network function is we're referring to as f, and we're claiming that the covariance between f and x on x and f on input x prime okay, so we should first claim that actually the expectation of f of x is 0, so that makes this thing the covariance. So the first claim number 1 is that the expectation of f of x is equal to 0, and claim number 2 is that the covariance is equal to h composed with ... composed with h of x transpose x prime over D. So D was the both the dimension of the input and also like the scaling factor for the input. And the number of times this H function is composed is L minus 1 times, where L was the number of layers. And we're going to call this thing is called, in the literature, it's called the compositional arc cosine kernel for Gaussian processes. So just to give you some interpretation of this result, like hopefully you're going to become familiar with it because you actually need to work with it to do the homework. But the idea is that this was the covariance structure of the linear neuron. It just depends on inner products in input space. But every time we add a network layer on top of the linear neuron, we modify this covariance structure by adding another function H. We compose another function H. So if you think back to the example with the trucks, you remember we were seeing some kind of structure that looks like it depends on input similarity. And I said that there's some kind of dependence on the inner products between input space. And Guanyo asked, like, what is that covariance structure? Well, the answer is, it depends a bit on inner products between input images in input space, but that covariance structure gets modified by the fact that you have this H function for every additional layer. And Yusong said that covariance looks remarkably correlated. Well, this H function is always positive. It takes negative inputs and maps them to positive numbers. So that explains why things always look correlated for the output of a relay network. But okay, let's just, I'll just finish, but if people have more questions about this, I'll stay on after.
Oh, sorry. I'll wait for you to finish.
Okay. So in summary, we found that for a finite collection of inputs, that the outputs of a wide neural network under random sampling of the weights is Gaussian, is multivariate Gaussian. And this is the statement that the neural network operates like a Gaussian process. And then the final slide, the point was that the covariance matrix, at least for MLPs, the covariance matrix of this Gaussian depends on how the neural architecture transforms the input correlations as measured by, like as measured by inner products in input space. Okay, our next lecture. So we've just introduced the tool, but it's not clear what you can actually use it for. Next lecture, we're actually going to take a break, giving you time to do the homework. And we're going to start talking about optimization next lecture. But the point is that we're going to, when we come back to generalization theory, we're going to start using this tool, which we just introduced this lecture. Okay, but yeah, that's it. So if anyone has questions, and I was like, maybe wondering if people would have questions about this slide, but anyway, thank you for listening.
Jeremy, this question is actually inspired by a talk by Professor Stefano Soato.
Yeah.
I'm wondering if you sample the weight from non-zero center Gaussian. For example, you kind of add a Gaussian perturbation on a well-trained neural network. Will the theory apply?
Yeah, I think it doesn't depend on the mean being zero. It simplifies the results if the mean of the distribution on the weights is 0, but I don't think it depends on that.
Right. So does that imply, so if you go back to the track figures, so suppose we are doing a random weight sampling on well-trained neural network, what would the correlation be?
Sorry, if we were doing this sampling, but you mean the mean of the weights was not 0?
Yeah, it's not 0. The mean is from a well-trained neural network.
Oh.
So given a trained neural network, we add a Gaussian perturbations on the weights randomly.
Right.
So yeah.
Yeah, that's interesting. Like, I mean, you would expect that the points in function, like that well-trained neural network is a point in function space, right?
Right.
So you would expect that that if the amount of if the variance of the distribution that you're sampling from is small, then the points in function space would cluster around that.
I think you have to shift the origin of function space to the output of the well-trained neural network.
Right.
You'd have to subtract, because the central limit theorem assumes 0 mean random variables, and the way you get around non-zero mean is you do a shift to 0.
Right.
So you'd have to, I'm speculating, although I'm fairly confident that you just have to mean shift the function space to where the origin is the output of the prior neural network.
Yeah. That's a great project. So the context of Guanyo's question is that something that people do in practice is they do fine tuning of neural networks. Like you have like 1 million images of cats and dogs, and you train an image classifier on the cats and dogs, but then you really want to do like breast cancer detection or something like that, where you only have a few hundreds or thousands of data points. So you want to take your cat dog classifier and fine tune it to do like something actually important. And then like Guanyo's question is like, how does this whole function space view like work around fine tuning? And yeah, like I think Yisong's suggestion is probably right, but like you need to check that. So that could be a good thing to look at.
I had a question, which was, are there closed form kernels covariance functions for all the standard nonlinearities?
That's a great question. I actually don't know. I just know that for NLP, that is one, and it's this. But if you don't, for other architectures, there may not be. But even if you don't have the closed form covariance function, you can still estimate it empirically, and that's what you're going to do on the homework. So even if you don't have a nice, it's sort of remarkable in a way that there is this nice closed form function, because if you look at the function, it's quite complicated. It involves like arc cosine and like these square roots, and the derivation is quite complicated. It involves some like weird integrals that you don't normally see. So it's quite cool that there is an analytical result in this case, but I think in general there isn't an analytical result for any architecture that you can think of.
So maybe a philosophical question. You started this lecture by talking about, what is the behavior of a typical neural network in this class of architecture, from this architecture class.
Right.
And in function space, this typical neural network is, a Gaussian distributed, it's a Gaussian process. Is there any insight of the structure of this kernel to the behavior of a typical neural network? Like,
yeah, I guess there's two comments. So one is that the functions you get from random, like if you actually train a neural network, you are going to end up with a function which is very different from the ones that you get from random sampling. but it's still like, this is sort of defining the prior on function space. But also like, yeah, so how do you interpret the covariance? Like, I think that is some interpretation of this covariance, because you can sort of see how you have just the standard inner product, but it's getting modified by the layers. And I think that probably, let's say, if you now try and derive a kernel for a convolutional network, you're going to see that somehow, it's not going to depend so much on inner products in input space, because that's like a basic vector inner product, and images don't have a vector structure. So what you would hope to see is that the kernel for the images depends on some like kind of better notion of similarity between images than dot products or transformed dot products. So that's what you'd hope to see. But I haven't written down I'm sure someone has, but I haven't written down the kernel for the.
Trying to see if derive it for a convolution neural network and seeing if it's like some sort of inner product over patches of the images or something like that.
Yeah. Something that, yeah. But that's a good point, that the overall point is that you can view this as the prior on functions is defined by this covariance structure, and it's somehow giving you a notion of similarity between inputs that gets modified by the network architecture. And yeah, we'll come back to that when we get to the Pack Bayesian generalization theory stuff.
Yeah, sorry, Jeremy, might ask like a broader perspective questions related to the cross project or something.
Yeah, of course.
So I think that maybe like in particular in applied math community, some people are thinking about like continuous viewpoint of neural networks. And they're thinking of them like applying some techniques like mean field analysis and maybe some other stuff to analyze the behavior of neural networks. So I'm just thinking of like, would it be possible for us to integrate stochasticity with like some continuous models to analyze the stability or maybe behavior of neural networks? Probably like could be like a bit of cross project or something.
Yeah, I don't have anything like great to say, but I think it sounds like a great thing to explore. Like another way that people look at continuous networks is like this like neural ODE thing, which was like, there's a paper on that recently. I don't know how that interplays with this, where that's like imagining that you have, instead of discrete layers, you have like a kind of continuous number of layers. But yeah, I think those would be really interesting things to look at.
Okay, cool, thanks.
All right, I'm going to stop the recording.